Hello guys, welcome to a video about permutations. So you are here to learn something about permutations, or for some other awkward reason, I don't know. On the board, I outlined for you what we're going to talk about today. So you can check that list and see if there's anything interesting for you. And if not, maybe you do not need to waste your precious time. Let me go through that real quick. First of all, we're going to talk about what is a permutation, obviously. That leads us directly to the question, how many permutations are there? We put them together in a symmetric group and explain that one. Then we introduce some further notions, like the sign and the inversion of permutations. Once we gathered all this understanding about permutations, we can start notating them down, introducing the common notations of Cauchy, cycle, and even the matrix notation. Then, once we know how to notate them, we can compose them. Finally, in 6, we test our notions and concepts on an example and see if it all works out, hopefully. What do you need for this? You need some understanding and familiarity with bijective maps, most and foremost. For maps, also you need sets, obviously, and the group, as in the symmetric group. Don't be afraid, you don't need to be an algebraic topologist, we just use the basic notion. And for the matrix in point 4, you need matrix calculus, but this is really not that important. You also see what I'm going to briefly recap and what not. Good. Before we start, let us quickly train our languages, like French.
Permutation.
Permutation. German.
Die Permutation.
Die Permutation.
Permutación.
Permutation. Greyjoy.
Permutação.
Permutation.
排列
排列.
Перестановка из n элементов.
Перестановка из блядь. Okay. That's for the languages. Let's go to
Leroy Jenkins.
point 1. What is a permutation? Okay, so the first and maybe the easiest way is just to think of it as shuffling. You have a set, like a deck of cards, and you shuffle it. You permute the cards. Like let's draw the kid's method of shuffling. You have carefully ordered your cards 1 through 6 over here. Then comes the kid, does all sorts of wild things. Shh. Everybody shuffled like this at once in his life, right? And then your 1 became a 4, your 2 maybe a 6, and so on. 3 stays. This is an example of a permutation. Okay. But we want to have a more precise language, the mathematical language, or the definition of a permutation. So what a permutation really is, I write it down first and explain the notions then. It is a bijective map, let's call it sigma, that's common notation, on the finite set A. Let's see if I can square this up. So this really is the basic definition of a permutation. So first of all, the finite set is your deck of cards. It's a set with distinguished elements, and yeah, if you don't believe it's finite, throw it on the ground, pick it up again, and you'll see it takes you only a finite amount of time. So it should have been finite. But what's the bijective map? Well, here I suggested you recap this before, but I will quickly help you. So let's pick a color here. So you have a set A. I draw the bijective map sigma. So the image space is also A. In A, there are finite amount of elements living, like 5. Obviously the same in the image space. Now you map each element to one element in the image space via sigma. It is important that you draw arrows to each point of the image space, but you hit each one only once. That's what a bijective map is. You see directly that you can go back and forth. It's each element gets uniquely assigned to another one. Yeah. So really what a permutation is, it's a bijective map on a finite set. That's all. Let's have some examples. So the first one is the one in A already, like A with the finite set. A equals the numbers 1 until 6. For example, sigma of 2 equals 6 in that example. Another one. This is the permutation, the shuffling I do when it's my turn shuffling. I sit down and do this. Okay, can we play? It's the identity map, doing nothing, or mapping each element to itself. This is obviously a bijective map, and it's a permutation, because the identity working on a finite set. Identity map with sigma of an element I being just the element I. One more, please. So there's one like fundamental permutation, which is called a transposition. It even got its own name. Fundamental in the sense because, as we will see, you can express any other permutations as a series of transpositions. But also fundamental in the sense of that it really does nothing. So sigma is a permutation if it keeps all elements or maps all elements on itself for all I in A except 2 specific elements, let's say K and L. What do we do with them? Well, we switch them, we transpose them. So sigma of K is going to be L, and sigma of L is going to be K. In terms of shuffling, you could argue that putting the last card on top and the formerly top card on the bottom is a transposition permutation where exactly these 2 elements got transposed and the rest stays the same. That's it for what is a permutation. We have a bijective map on a finite set. We have a specific one, which is the transposition. And we have the one which is doing nothing, which is the identity map. Now, The question which sort of immediately arises here is, well, okay, I have my set. I have some sort of permutations. In how many ways can I permute this set? How many permutations are to be found on this set? In how many ways can I shuffle? How many, my friend? How much? How many permutations exist? Yeah, never mind. Am I an English teacher? No. Exist on A. And that leads us to the notion of the symmetric group in just a minute. Symmetric group. So first, let me try to draw a line here. Easy. Okay. How many are there? Well, let's figure this out together. It really is the old question, same old question. And how many people? Let's have n people. How can we place them on n seats? In how many ways? So that's permuting them. Or having n cards. In how many ways can we bijectively map this to the same set of n cards? Okay. Yeah, well, how many? You probably figured it out already, but let me explain anyway for those who haven't. So let's pick a card. I picked some cards here which are not numbered, just to show that it doesn't depend on the numbers. It's just distinguishable elements. For example, first element would be the awesome helmet. So let's map this awesome helmet to another element of the set. For example, we map it on the magic projectile. Okay, now pick the next one. What about the boots for running away really quickly? On how many elements, from how many elements can we choose where we map this one on? Well, the magic projectile is already gone. So we are left with n-1 possibilities. Let's notice. So first element had n possibilities. Of course, I should say that A has n elements. The second one has n-1. The third, n-2, and so on. And now if we combine all these possibilities, we essentially have to multiply them. So what we're getting is n times n-1 times n-2, and so on, times 3 times 2 times 1. Yeah, you could leave out the 1 in the end, but for completeness. Okay, what is that? Well, you calculated at home. Oh, wait, n is a variable. But we have this expression here, n exclamation mark, which essentially means the thing which is written on the left. It's n faculty. So this is the number of possible permutations on a set A with n elements. Now, let's make a set, not of these elements in A, but a set of all permutations. And let's give this a name. Set of all permutations. And let's call this one Sn the symmetric group. So the symmetric group contains all ways to shuffle this deck. Like how many permutations are there on a deck of 32? Would you guess? Let's calculate this real quick. 32. Oh, it's only 2 times 10 to the power of 35. Sure. So in order to become a perfect shuffler, knowing all permutations there are, you probably need some time. But putting all of them together, we have the symmetric group. Now, here you ask, well, why is it called group? Isn't that a special thing in math? Well, it is. That's why I mentioned it in the beginning. And I also said I will quickly recap on this too. So a group is basically a set with a composition, and it has to fulfill 3 additional laws. So the first one, it has to have a neutral element. So what is the neutral element of Sn? Well, here you obviously need to know what a neutral element is. The neutral element is the one which you compose with another element of the group, and you still get the other element. So let's call this one n, and let's compose this one with sigma, and we should get n. Now, what composition are we actually talking about here? Well, we are really talking about shuffling ones. This is one permutation. The circle is the operation. We take, let's say, sigma. You put in 2 permutations like sigma and tau, and these ones get mapped on a permutation, sigma, tau. Well, okay, that helps you a lot. That's like a formal way of writing it down. But that essentially means, I write it down for the neutral element, that you first apply sigma on an element I, and then on that element you apply n. That's it. So what is the neutral element? The way of shuffling, which you could apply after or before another way of shuffling, and you don't change anything. Well, we had it already. N is identity map. Okay. Then what else do we need for the group? We need an inverse element for each element in the group. What does that mean? That means, let's have one element. This is the set A. This way, that was one permutation. Let's call it tau. What's the inverse element for tau? Well, it is undoing this permutation, which was maybe something like this. I don't remember. But it is obvious. Once you have some sort of reordering, you can always redo this on a finite set. And this sorting back to the original order, so to say, that's the inverse element. So we have this one. And then we need associativity for a group. Associativity, essentially sigma pi tau should be the same like pi tau. And that's fulfilled, that's fine. Okay. We could have a commutative group. an abelian group, but we don't have it here. What would that mean? So I make an attention sign, composition of permutations, usually not commutative. So no, Sn is not an abelian group. Why is it not commutative, or what would that mean? That means you shuffle in a certain way. Let's say you just do this. Your friend shuffles in another way. Let's say he does this. Now, if permutations and shuffling would be commutative, it wouldn't matter if you start doing this and let then your friend shuffle like this, or the other way around. But obviously, that's not the same result in the end. So here we do not have commutativity. Fine. Yeah, that's all about the symmetric group for now. We can now directly go to more notions concerning permutations, which is the sign of a permutation and inversions. Well, let's actually introduce some more space here. Okay, and also align. So let's start with the inversion. Now there's maybe some inversion guys upon you. This is not so much the classical inversion or the way we use this notion in other fields, but it's much easier. Inversion. So what's happening? Oops. What's happening is that let's have a pair, or what we need is A is an ordered set right now for these notions, sign and inversion. An ordered set means it's a set where you actually can say that one element is bigger or smaller than the other one. Example would be rational numbers. An example which is not ordered are complex numbers. So let's assume we have one of those. Then we can say an inversion is the following. Let's have a pair I and j. Both living in A, of course. And we say I smaller j. So here we have the ordering, what is bigger, what is smaller. So we have a pair like 3 and 4, where 3 is smaller than 4, but the permutation of I is bigger than the permutation of j. That's all. So let's say we map 1, 2, 3 with sigma. We leave 1. We do this. We map 1 to the 1, 2 to the 3, 3 to the 2. Then 2 smaller 3, but sigma of 2 equals 3 greater 2, which is sigma of 3. So that's that pair of values I and j in the pre-image space is the inversion. Good, just so that we know. Nothing fancy about it. Let's talk about the sign. So the sign is basically, as the name says, plus and minus. So we can assign a sign to permutations on ordered sets. How do we do that? Well, we say signum of sigma, the sign of sigma, equals -1 to the power of r, and by r counts the number of inversions. That's one way. I will do an example in a second. Another way, we can say the signum of the permutation equals -1 to the power of t, with t the number of transpositions with which we can model the permutation. So maybe you remember in the beginning I said we can actually express any permutation as a composition of transpositions. Transposition was that simple permutations where you just switch two cards. So if you reorder the set in any way you want to, I can find a way by only always switching two cards at once, and I will reach the same final state as you. So, and if this is like an even number, then we get a plus sign for the permutation. And if it's uneven, or I mean odd, we get a minus sign. That's all. So let's see. Let's have 1, 2, 3, 4. And we map this to 4, 2, 3, 1. Let's first count the number of inversions. Let's, for example, start with 1 and 2. But sigma of 1 equals 4, which is greater than sigma of 2. Okay, so that's 1. 1 and 3, same thing. I leave this for you. 1 and 4, also an inversion. So you see the pair of values doesn't have to be next to each other, so to say. 1, 4. Then there's also 3, 4. Sigma of 3 equal 3 greater than sigma of 4, which is 1. I hope I didn't forget anything. Well, that's it. Okay. 4 inversions. So R, which was the counter of inversions, is 4. And therefore, the signum of this permutation sigma -1 to the 4 plus 1. Easy katka. Yeah, I think that's enough for sine and inversions. These are really just small little names, so to say, for specific permutations on ordered sets. Yeah. With that, we can now finally go to some serious notation business, which would be point 4. Let's recap real quick what we did. We figured out what is a permutation. Let me write this down. Notations. And let's make a line. Very nice. We figured a permutation is a bijective map between on a finite set, or shuffling. Then we found some examples. Then we figured that taking all permutations on this particular set with n elements gives us a symmetric group, actually an algebraic structure. Then we went to ordered sets, like regular numbers, and we found some more notation, some more notions like the sign. But the real interesting stuff right now is, well, talking so much about permutations, what is the best way to note them down, to write them down? And as it turns out, there are different ways. Like the first one is the Cauchy two-line notation. This is maybe the most intuitive one, or the most basic one. Now, before I explain this, let me quickly write down the other ones. From the Cauchy two-line notation, there's also a one-line notation, deductible, where you basically just leave out unimportant stuff. Notation. Then the very famous cycle notation. And last but not least, the matrix notation. This is where I said you might need some matrix calculus, but it's really just a brief third method. The first two ones are the essential ones. All right, let's start with the Cauchy. So I basically used the Cauchy notation before, like up here. But the way you would write this down correctly, so to say, or the most common way, would be to place the pre-images up here. Make two brackets, spacing two lines, and write the images below. So let's invent a permutation on the set of 1 through 5. Oh, that was wrong. Scusi. That's it. That essentially means sigma of 1 equals 4, sigma of 2 equals 1, and so on. Yeah, that's all about the Cauchy notation. Now you can say, well, assuming that the first line is put down in 1, 2, 3, 4, 5, I could also leave out the first line and just write the second one. That would be the one-line notation. Saying that we assume that it's written in the correct order, It's really important because, so this was sigma, but it doesn't depend on the order of the pairs. Like for example, if I put 2, 1 in the beginning, then 1, 4, 4, 3, 5, 5, 3, 2, this is still sigma. Very important, because sigma tells us on which element gets mapped. So like sigma of 1, the 1 gets mapped to the 4. Never mind if it stands in the first position or the second one. So this is really important. You could also order this like 1, 2, 3, 4, 5 below and write down, let's see, 2. Try this for yourself. Yeah, looks good. Yeah, that's it. So that's the Cauchy notation. If we use the one-line notation, we just write down 4, 1, 2, 3, 5, assuming that everybody accepts or expects that the 1 is mapped to the 4, the 2 to the 1, and so on. The 1 to the 4, the 2 to the 1, 3 to the 2, and going on like that. Now there's another funny way to note down our permutations, which is, there was one, the cycle notation. Yeah, this is maybe, these two are maybe the ones you already knew or you have seen before, but let's explain them carefully. My PC is a little slow in this second, not scrolling my stuff. Okay, for the same sigma, we do brackets. We start with a bracket. We pick one number, for example, the 1. So what do? You take arbitrary element from A and write open bracket this element. Let's call it X. Then now you add the image of exactly that element X, like bracket X sigma of X. In our example, this would be 1. The 1 is mapped to the 4. Now you do the same thing again. Sigma of this element before X, sigma of X, sigma of X. Side note, if you are confused why I can put sigma of X into sigma, like basically putting the image space into the pre-image space, then you should remember that we have a bijective map from A to A. So each element, sigma of X from the image space, I can put into the pre-image again. All right, so the 4 gets mapped to the 3. Now you continue continue until you reach x again. That would be x, sigma of x, sigma of x, and so on. But you leave out, final x, so that you basically reach the beginning again. So let's see, 1, 4, 3. 3 gets mapped to the 2. 2, we are here now. 2 gets mapped to the 1. Now we reached our beginning number 1 again. And now we close the bracket. And open a new one for the rest. Because there's still numbers which didn't appear in this thing over here. Which one is missing? Well, the 5. The 5 is mapped to the 5, so I cannot write down the 5 again, because it's the beginning number. I close the bracket. And since this last term is like an identical term, 5 to the 5, we conventionally leave this out, the whole thing. So let me add as point 4. Start with I for an element which hasn't appeared yet. Fine. So there was one last one, the matrix notation. So what we want is we write the set as a vector. So we write all elements of the set A in a vector X. We apply a matrix P for permutation or something else. And we want to get sigma all images, so to say. So let's fill this out. X would be 1, 2, 3, 4, 5. Sigma of 1 was 4. Sigma of 2 was 1. Of 3 was 2. 4 was 3. 5 was 5. Now, which matrix maps this vector x on sigma of x? Well, this we can really, of course, you need to know how to apply a matrix to a vector. That's why I said you need very, very little bit of matrix calculus. But let's see. So we have line times row. So we put 0 times 1 plus 0 times 2 plus 0 times 3 plus 1 times 4 plus 0 times 5. Oh, did I write some? Made a mistake in the image vector here. 3 gets mapped to the 2. 2 gets mapped to the 1, obviously. Mi scusi. Okay. So for the 1, we get 1 times 1 and zeros everywhere else. The 2, we put the 1 at the second position. The 4, the 3, we put it at the third. And the 5th on the diagonal. Fill everything out with zeros, and there you go. And this is your permutation matrix P. So there's also no magic involved. And the most common notations definitely are the Cauchy or the cycle notation. And that's the ones we will use for the next point, which is composition. Chapter 5. The question is, how do we compose two permutations, the 2 times shuffling? How do we write this down? Okay, we're looking at the composition of permutations, meaning we're shuffling 2 times. So let's introduce 2 permutations. Let's call one permutation pi, which does the following: 1, 2, 3, 4, 5 in Cauchy notation, 2, 3, 4, 5, 1. And the second one, tau, which is acting like 1, 5, 2, 4, 3. They both act on the same map, same set A with the elements 1 through 5. Okay, so let's, for example, pick one element. Well, let's say what we're doing is pi composed tau, meaning first execute tau and then pi. So let's do this for one with some values, for example. For example, let's take the 1. So tau of 1 equals 1. Pi of the result 1 equals 2. So pi after tau of 1 is gleich, sorry for the German here, equals 2. So in a way, if we have pi after tau noted like this, we have to write down 2 over here. And the same goes for all other numbers. For example, the 3 becomes a 2, whereas pi maps a 2 to a 3. So in the combination, actually nothing happened to the 3, because tau mapped it to the 2 and pi mapped it back to the 3 equals 3. And you can fill in the rest. Another way you can do this, you can write down, and that's even easier, first pi, the one you do first, which is tau, 1, 5, 2, 4, 3. Now you prolong this bracket, and below that you write pi. But now you have to be careful, because you have to, okay, for the 1 it's easy. The 1 gets mapped to the 2. But here you have to pick the 5. Look at what happens to 5. It gets mapped to 1. And put this one in. What happens to a 2? It's a 3. So this is basically this bracket, but rearranged in another order. But the pairs are still the same, so the mapping is the same, independently of the order. Remember in the beginning, at the Cauchy notation, we said the order is not important. So here a 4 gets mapped to the 5 and a 3 to the 4. Let's check with this. So this was tau, this was pi. And combined, we should get the same as on the right hand side. Should get 2, 1, 3, 5, 4, and at least for the two numbers we tested, that's the same. All right. So that's composition in Cauchy and in cycle notation. It was in Cauchy. In cycle, we do the following. We write down, first of all, we have to get the cycles for the two permutations. So let's start with tau. Start with a 1. 1 gets mapped to 1. Okay, damn, that was bad. Start with a 2. 2 gets mapped to the 5, 5 to the 3, 3 to the 2, that's it. And 4 stays the same. So all in all, this is 2, 5, 3. And the same for pi. If this is too fast for you, you can obviously slow down here. Pi. 1 gets mapped to the 2, 2 to the 3, 3 to the 4, 4 to the 5, and 5 to the 1. And now we want to do pi composed with tau. So writing this down again. 1, 2, 3, 4, 5. 2, 5, 3. How do we do that? So here what you do is you pick, for example, pick element in tau, for example, the 2. Ask where the 2 is going to. It's mapped to 5 in tau. Now 2 gets mapped to, or let's write it differently. Let's write tau of 2 equals 5. Now look for 5 in pi. Pi of 5 equals 1. So essentially, in the composed permutation, 2 gets mapped to the 1. And now let's look for the 1 in start with I again. Start again in tau with the result 1. There's no 1, so that's 1 is left as it is. Let's look this up real quick. In tau, yeah, up here. So that's right. And now 1 gets mapped to the 1, and in pi, 1 gets mapped to the 2. So this one gets all in all finally mapped to the 2 again. So we can close this bracket. Easy. Then next one. Why not take the 5 over here? So the 5 gets mapped to the 3 via tau, and the 3 gets mapped to the 4 via pi. Then the 4 is left identical in pi. So I could say to the 4 in tau, I'm so sorry. And in pi, it's mapped back to the 5, so I can close the bracket. No, there's only the 3 left, and although I know that the 3 has to be mapped to itself, because in 5 numbers, there's just a 3 left, but I'm gonna write it down anyway, so some more space. 3, so the 3 gets mapped to the 2 in tau, and the 2 gets mapped to the 3, and so this is 2, 1, 5, 4. Yeah, that's composing composing permutations in the different notations. And what's important here? Yeah, important really is, like in the cycle notation over here, that you look, once you have the 5, you look in the next permutation. So the 5 in the permutation tau gets touched only once, because it has one image. And we have to take this image and put it in the next permutation, in the next map, and look what image is created there. Okay. With all that, I think we're ready for the top deck to the bottom example. Let's see. Yes, we are. So this would be 6. Example. Top deck card to the bottom. And what I'm particularly interested in is, first of all, we take a set of cards with n cards. Then we note this down in all the notations, all the 3 notations we have. Cauchy, cycle, matrix. What else? We ask for how many inversions do we have? We ask for the sign of this permutation, this particular one. And then what we finally do, we write this whole permutations as a composition of transpositions. Remembering from the beginning that we can write every permutation as a composition of transposition, that is only doing twofold switches of cards, one switch at a time until we reach the final state. And we said it's possible for every permutation, so let's check out if it's possible here, or it should be. Okay, so what's the example? Well, I wrote it down there already, but like sigma of 1 equals n for n cards, and sigma of every other card equals the card before, right? Because the first card 1, let's say the first card is the 1, becomes a 2. So in Cauchy, let's see, Cauchy, maybe this is a little more intuitive. So we have 1, 2, and so on until n. So the top deck card is the 1. Gets to the bottom. So the last one is mapped to a 1. The first one is mapped to a 2. 2 is mapped to a 3. And so on. And the n-1th card is mapped to n. Okay, that would be Cauchy. Now the cycle notation. So let's start with the 1. First card. It gets mapped to the second. Second is mapped to the third. And so on. Until the nth card, which is mapped to the first one. So I can close my cycle over here. I didn't miss any cards, so that's it. Very nice. Finally, the matrix. So we're multiplying the matrix with the vector 1, 2, and so on until n. And we want this 1 to be placed back there. Or let's say, what do we want to have here? We want to have 2, 3, and 1. So really, for the first line, we want to get a 2. So we want to do 1 as 0, 1, and zeros, which comes down to 0 times 1 plus 1 times 2 plus 0 times the rest. So that's fine. Okay. Next is we want to have 3. So we need to hit the 3 over here with a 1. And so on. You see that the 1s will follow this off diagonal or the side diagonal. And last line is interesting again. We want to have the 1. So there's the 1 from the beginning. That's it. So this is really a matrix where, like the unit matrix, where the first line, the first row, is put down on the bottom. Yeah, that looks good. All right. We wanted to ask the number of inversions for this permutation. Here we remember that inversion was a pair of values, I and j, where the image of them is reversed order. Then if I was smaller than j, then sigma of I is bigger than sigma of j. So let's see what's happening here. We have sigma of 1 is 2, sigma of 2 is 3. That's fine. Basically, it's all fine, but this one. So for example, 1 smaller than n, but sigma of 1 equals 2, and which is smaller than sigma of n, which is smaller. Obviously it's bigger. So those two signs, this one and this one, are reversed, so that's an inversion. So basically, sigma of n is smaller than sigma of all I not equaling n. But n is bigger than all I not equaling n. Therefore, how many inversions do we have? You count them. I wait. Ready? Okay. So, well, obviously we have n minus 1 inversions, because all numbers here are bigger than the last one. But the part before the 1 in itself it's fine. It's ascending order, like the pre-image space here in the first row. Okay, so we found the number of inversions. By that, we already know the sign or signum of this permutation sigma, which was, no, looking back, no, it's -1 to, I think we had r to the power of r. So it's -1 to the n-1. So it really depends on the amount of cards in your deck. It is +1 for n odd and -1 for n even. Usually you play with a, let's say, a 32 deck, and then this permutation would be to have the sign -1. Yeah. All right. We got inversions, the sign, and now let's talk about transpositions. Transpositions. Sigma equals tau m after tau m m-1 and so on until tau 1. So with tau e, the tau I, the ith transposition. Okay, now we have to find those taus. Hope we find something. Alrighty. Well, let's do some thinking here. What can we do? I write down the Cauchy version just to have it here and do not have to scroll. 1 became the 2, 2 became the 3, 3 to 4, and so on. n-1 became the nth element, and n was mapped to 1. So we're essentially shifting the whole set 1 to the left. Okay, so how can we do that? Just by transposing. Well, here there's definitely more than just one method. So that's absolutely non-unique the way permutation can be expressed as transpositions. So let's find one or two. For example, let's say we start with tau 1 being changing. We want to get the 2 over here. So 1 becomes a 2, and then we unfortunately get the 1 over here. I put this in a small 1. So next one, we want to make this 1 over here a 3. So 1, 3. You probably already see the pattern. So the 3, but then the 3 is a 1. But we want to have a 4 over here. And so on until we're addressing the n-1 element, which has become a 1 from the transposition before. And we want it to be an n. And the nth element is mapped to the 1. That's it. So sigma equals 1n composed with 1n-1 composed with the first one to start with 1, 2. Now, there's also a way in cycle notation, leaving out those compositions, but there we have to pay attention to the direction, because in composition language, you always start with the last one. In cycle notation, you just go regularly from left to right. So here we would have to do 1, 2, 1, 3, 1, 4, until 1n. So this is composition of permutation maps. And this line is cycle notation of one permutation, but where all parts are transpositions. I hope that helps and doesn't confuse. If you want to, you can come up with any other transposition compositions. I'm fine with that for now. And let's see, we did the top Descartes to the bottom example, yeah. So let's not lose track of what the goal was. The goal of the whole thing was obviously permutation basics, and the goal of this example was to find all three notations, talk about inversions, talk about the sign determined by the number of inversions via this formula, and also show that in fact we can formulate this map of the permutation, the sigma map, as a composition of transpositions by finding a pattern of transpositions like this. And yeah, of course, from that we could also again assign the map sigma a sign over the other formula, which was -1 to the number of transpositions we needed, which, as you can see over here, as I counted 1, 2, 3, until n-1 to the n-1. So that's the number of transpositions, which was t, I think. And it equals the -1 to the r. So this is not contradictory, and that's fine. That's what we wanted. Very nice. So yeah, thank you very much for listening. I hope you got some insights into this very fundamental thing of permutations, shuffling, whatever you want to call it, bijective maps on finite sets. And yeah, enjoy. And if we have anything to add or ideas how we could improve the whole thing, just leave it in the comments, and I see you next time.